Hi, in this particular presentation, I am going to discuss the topic of asymptotes, which plays a very important role in understanding the shape of a curve based on its equation. So to begin with, we'll understand what an asymptote is. We define the asymptote as follows. An asymptote to a curve y equals f of x is a tangent to it at infinity. Or in other words, we could say that an asymptote to a curve is a line whose distance from the curve approaches 0 as either x approaches infinity or y approaches infinity or both. Of course, this might not convey the exact meaning of what an asymptote is. So to understand that, probably we'll take up a few examples. To begin with, we'll take up the hyperbola whose equation is xy equals 1. If you remember, this equation represents the rectangular hyperbola xy equals 1, whose shape is as follows. So this is how the curve y equals 1 by x or xy equals 1 looks like. As I said, this is a rectangular hyperbola. So if you look at the curve and observe carefully, you see that the curve looks as if it is going to touch the x-axis and the y-axis as x and y keep on increasing. So as you can see, as we increase the values of x and y, the curve goes closer and closer to both the x-axis and the y-axis. So as x approaches infinity and y approaches infinity, we see that the curve gets as closer to the x-axis and the y-axis as possible. Accordingly, we see that the x-axis and the y-axis are both asymptotes to this particular curve, which is the rectangular hyperbola xy equals 1. So basically, what do we mean by asymptote? It is basically a tangent to the curve which looks as if it touches the curve at infinity. And when I say at infinity, it means to say that you have to take either x equals infinity or y equals infinity or both. Okay, so to make things much more understandable, I would like to give another example. The next example would be about the curve y equals tan x. I'm talking about the tan function, trigonometric function. So we look at the graph, the function y equals tan x. As you can see here, this is the graph of the tan function, tan x. So as you can see, from minus pi by 2 to plus pi by 2, the graph of tan x is like this. And because it is a periodic function of period pi, it repeats itself after every period of pi units. So this is the graph of y equals tan x. Now, do we have an asymptote for tan x? By looking at the graph, I think it is easy to observe that this line, as you can see, touches the curve on either side at x equals pi by 2. What I'm trying to say is that as x approaches pi by 2, this curve, as you can see, there are two branches of the curve. So these two branches of the curve look as if they're going to touch this particular line as x goes closer and closer to pi by 2. So when x approaches pi by 2, we see that these two branches of the curve meet the line x equals pi by 2. So accordingly, x equals pi by 2 is going to be an asymptote to this curve. And if you observe, it is, I think, very obvious that it's not just x equals pi by 2 is an asymptote. X equals minus pi by 2 is also going to be an asymptote. X equals 3 pi by 2 is going to be an asymptote. X equals minus 3 pi by 2 is an asymptote, and so on. So in general, y equals 2n plus 1 into pi by 2. I think it is supposed to be x. I'm sorry. So x equals 2n plus 1 into pi by 2, where n is any integer, is an asymptote to the curve. So for the curve y equals tan x, there are going to be infinitely many asymptotes, each of which is parallel to the y-axis. Correspondingly, it has its equation as x equal to a constant, and that constant is an odd multiple of pi by 2. Right? So I hope that these two examples have made you understand as to what asymptotes are. So now we'll see how to find the asymptotes to any curve if they exist, if it exists, based on some working rule. Of course, it is very important for you to understand that not every curve will have an asymptote. So if the curve has an asymptote, we are supposed to find it, and how to find it is what I'm going to explain in the next part of this presentation. Okay, so I'm going to give you what is known as the general rule to find all possible asymptotes to the curve y equals f of x. So how do we do that? First of all, we classify the asymptotes into two types. One set of asymptotes which are basically parallel to the coordinate axis. I mean to say that we are looking for asymptotes parallel to x-axis and asymptotes parallel to y-axis. So we will first find them, and finding them is going to be pretty easy as such. I'm going to explain how. And after that, we'll see how to find out asymptotes which are neither parallel to x-axis nor parallel to y-axis. And such asymptotes are known as oblique asymptotes. So I'll come to that a little later. So to begin with, to find asymptotes parallel to x-axis, of course, once again I'll repeat this. If there are asymptotes to the curve, we're going to find them based on the following rule. Okay, so if you look for asymptotes parallel to x-axis, they are obtained by equating the coefficient of the highest degree term of x in the equation of the curve to 0. What do you mean with this? We'll probably understand the meaning of this based on few problems. So right now I'm going to highlight this part. So we'll have to equate the coefficient of the highest degree term of x in the equation to 0, and that will give me asymptotes parallel to x-axis. Right? Likewise, if we have to find out the asymptotes parallel to y-axis, we will just have to equate the coefficient of the highest degree terms of y, the coefficient of the highest degree term of y in the equation to 0. So first of all, look for the highest degree term of x and equate its coefficient to 0, and that will give you asymptotes parallel to x-axis if any. In the similar way, equate the coefficient of the highest degree term of y to 0, and that will give you asymptotes parallel to y-axis if any. Okay, so this is how we find out the asymptotes parallel to the coordinate axis. Now we go for the next part where we find out the oblique asymptotes. I repeat, oblique asymptotes are those asymptotes which are not parallel to the coordinate axis. So these asymptotes are neither parallel to the x-axis nor parallel to the y-axis. Okay, so to find these, we have a set of rules, we have a certain number of steps which have to be followed. So first of all, we assume each of such an equation of an asymptote of the form of y equals mx plus c, because basically any asymptote is a straight line. So y equals mx plus c, we assume that to be the equation of the asymptote. So the rest of the process would be to find out what m and c are. Of course, as we know, m represents the slope of the line and c represents the y-intercept. So we'll see how to find m and c based on the following steps. So how do you do that? First of all, step 1, group the terms in the equation of the curve based on the degrees, that is in powers of both x and y. That means in the equation of the curve, what you are supposed to do is you have to group all possible terms of certain degrees. Say degree 1 terms, degree 2 terms, degree 3 terms, and so on. Okay, and then after that, in each term of degree k, when I say degree k, it could be degree 1, degree 2, degree 3, and so on. So what we are supposed to do is we'll have to replace every y by m and every x by 1. So simply take every y as m and take every x as 1 and call that expression as phi k of m, where k is the degree of the corresponding term. And once you have got phi k of m, you will have to find out phi k dash of m. You will see why you have to find out this later on. Okay, this is the step 2. Then when you go for the step 3, take phi n of m to be equal to 0, where n is the highest degree in the given equation. I repeat, as you can see, we have got phi 1 of m, phi 2 of m, phi 3 of m, and so on. So in this, look for the highest degree term, and that n, that highest degree, take it to be n, and take phi n of m to be equal to 0. Right? So this will be an algebraic equation of degree m. So of course it will have m. This will be an algebraic equation of degree n. So this will have n roots, and each of the roots will give you the corresponding value of m. Now, based on what m is, we'll find out the corresponding c's in the next step. So how do we do that? So here we take up specific cases. Suppose m is a distinct root. When you say distinct root, you are supposed to get m as a totally different root altogether. It should not be a repeated root, is what I mean to say. So if m is a distinct root of the equation, then the corresponding value of c is obtained using this formula. Looks a little complicated, but I'll explain this when I go for solving a particular problem. Okay, so c is given by minus phi n minus 1 of m by phi n dash of m, where n is the highest degree in the equation. Similarly, if we have m to be a double root, when I say double root, I mean to say that m is a repeated root. Okay, and in such a case, because m is a double root, there are going to be two c's, and those two c's are obtained by solving this equation: c square by 2 factorial phi n double dash of m plus c into phi n minus 1 dash of m plus phi n minus 2 of m equal to 0. I'll explain this once again when it comes to problems, so don't worry much. Similarly, if m is a triple root, m is repeated twice, is what I mean to say, thrice I mean to say. So if that happens, then there are going to be 3 values of c, and those values of c are obtained using this expression. And this procedure continues based on the multiplicity of m. Okay, so this is exactly how we find the values of c corresponding to the values of m. So once you have got c's and m's, the corresponding asymptotes are given by y equals mx plus c. Right? So this is the general working rule to find all possible asymptotes to the given curve if they exist. Okay, so this is the whole procedure. Now before we move on to problems, there's one thing that has to be remembered very importantly, and it is that if the highest degree term of the curve has degree n, you will have to know that the curve has at the most n asymptotes. What am I trying to say here? If the highest degree term in the given equation of the curve is say 3, then the curve has at most 3 asymptotes. If the highest degree term is 2, then the curve has 2 asymptotes, and so on, is what this means. This point is going to be very important, because if suppose the highest degree term of an equation of a curve is say 2, and suppose we have got 2 asymptotes already, then there is no point finding more asymptotes, because there cannot be more asymptotes, because the curve has at most n asymptotes, where n is the highest degree of the equation. Okay, now we will see how to find asymptotes of a given curve based on some examples. So to start with, we'll see how to find the curve asymptotes to the curve x square y square equals a square into x square plus y square. So to begin with, as I have told you, first we'll find out the standard asymptotes. When I say standard asymptotes, I mean to say that we will find the asymptotes which are parallel to x-axis or y-axis if they exist. Okay, so for that to be done, First of all, we will rewrite the equation in such a way that we have it in powers of x and powers of y specifically. So x square y square minus a square x square minus a square y square is what I have as the equation of the given curve. Okay, now once I've got this as the equation, to begin with, to find all possible asymptotes parallel to x-axis, so to find this, what we do is we will just recall as to what is to be done. So to find asymptotes parallel to x-axis, equate the coefficient of the highest degree term of x in the equation to 0. What do you mean by that? Look for the highest degree term of x in this equation. As you can see, we have an x square term here, we have an x square term here, and a constant term here because there is no x here. So there are only two terms involving x and both are of degree 2. So these are the highest degree terms. Okay, so what we'll now do is that we will equate the coefficient of these two terms together because these are the highest degree terms in x, and we'll equate the coefficients to 0. So accordingly, what do we have? We have the coefficient of x square as y square, correct? And the coefficient of x square here is minus a square, and we'll take that equal to 0. And if we solve this, we're going to see as to what the asymptotes parallel to x-axis are. So of course, solving this will give us y to be plus a and y to be minus a, correct? So now we'll say that thus the asymptotes parallel to the asymptotes of the curve specifically, I would better write that way. Asymptotes parallel to the x-axis are y equals a and y equals minus a. Right? So this is how you find out asymptotes parallel to x-axis. Okay. Now in a similar fashion, we'll now go for finding the asymptotes parallel to y-axis. Okay. So when you go for asymptotes parallel to y-axis, what should you do now? As we went for asymptotes parallel to x-axis, now we'll look for the highest degree term or terms of y and equate the corresponding coefficients to 0. Now what are the terms involving y? So this is one term containing y and this is the other term containing y, and as you can see both are of degree 2. So the highest degree terms in y are this and this. Correspondingly, take the corresponding coefficients of these two terms and equate that to 0. So the coefficient of y square here is x square and the coefficient of y square here is minus a square. So equating those to 0 will give us x equals a and x equals minus a. Right? So accordingly, now we conclude that the asymptotes of the curve parallel to y-axis are x equals a and x equals minus a. Right? So these are the asymptotes parallel to x-axis and y-axis. Now we'll have to go for finding the oblique asymptotes to the curve. But before that, I would like to recall the note that I gave you before we started off with the problems. So as you can see here, if the highest degree in the equation of the curve is n, then the curve has at most n asymptotes, is what it means, is what it says. So accordingly, as you can see here, if you look at the equation as a whole, and if you look at the degrees of each of these terms, now when I'm talking about the degree now, I'm talking about the degree of both x and y put together. Okay, now the degree of this term is going to be 4, the degree of this term is going to be 2, and the degree of this term is going to be 2. So what is the highest degree? The highest degree is 4. So that means that since the curve, since equation of the curve has highest degree to be 4, what does it mean? There are at most 4 asymptotes to the curve. Correct? So there are going to be only 4 asymptotes to the curve. Now, because there are only 4 asymptotes, and as you can see here, we got 2 asymptotes here and 2 asymptotes here, we have already got 4 asymptotes. So there is no possibility of us having any further asymptotes. So I would simply say that there are no oblique asymptotes to the curve. I repeat, because the highest degree term has degree is of degree 4, accordingly there are a maximum of 4 asymptotes, and because we have already got 4 asymptotes, there is no point finding oblique asymptotes because we have already got all the 4 asymptotes. Okay, I hope I have made you understand this particular part. So because of this, there is no point finding the oblique asymptotes for this particular curve. I repeat once again, suppose by chance we had got only one asymptote here and say an asymptote here, then we would have got only 2 asymptotes, and in such a case we might have got further oblique asymptotes, and for that to be done we should have gone for this particular procedure to find general asymptotes. Okay, but in this particular problem there is no point going further because we have already got all the 4 asymptotes. Okay, to make you understand things better, probably we'll take up the next example again. Now let's say the next example. Now I'm taking up this particular curve whose equation is y cube minus x square y plus 2y square plus 4y plus 1 equals 0. Okay, so the question is about finding all the asymptotes to this curve. Okay, so how do we start? So once again we begin rewriting the equation by multiplying term by term and writing all the terms on one side. Now the equation is already given in this particular form. Okay, so there is nothing much to be done when it comes to rewriting the equation. So this is the equation that we have. So to begin with, first of all, I would straight away claim this. There are at most 3 asymptotes to the given curve. Why? It is because, as you can see here, the degree of this term is 3, the degree of this term is 3, and the degree of this term is 2, the degree of this term is 1, and the degree of this term is 0. So what is the maximum degree term? It is this term or this term, and because both are of degree 3, I can claim that the equation is of highest degree 3, and accordingly there are at most 3 asymptotes to the given curve. Why is this important? It is because if we are able to find 3 asymptotes which are parallel to the coordinate axis, then there is no point finding any other oblique asymptote. Okay, so now the question is, can we find out 3 asymptotes parallel to the coordinate axis? So for that to be done, we will first start with asymptotes parallel to x-axis. So how do we find them? So for that to be done, what we'll do is we'll first look for the highest degree terms in x. Okay, so I repeat, what should we do now? To find asymptotes parallel to x-axis, we have to equate the coefficient of the highest degree term of x in the equation to 0. Okay, so coming to the equation, now we are supposed to look for only the degree of x. So in this, what's the degree of x? There is no x term at all, so the degree of x is 0, and in this the degree of x is 2. In this there is no x term at all, so the degree is 0. Again here the degree of x is 0, and here the degree of x is 0. Now out of these, which is the highest degree term of x? Obviously it is this term minus x square y. So to find asymptotes parallel to x-axis, we have to equate the coefficient of the highest degree term of x to 0. And what is that coefficient? It is basically minus y, right? So equate it to 0. Or when you say minus y equals 0, it simply means y itself is 0. So now, because this automatically is the equation of a line, we can now claim that the asymptote parallel to x axis is y equals 0. And what is y equal to 0? Basically it is nothing but the x axis itself. Okay, so as we can see here, this is the only asymptote to the curve parallel to x-axis. Okay, so now we have got one asymptote. Now we'll quickly move on to finding the asymptotes parallel to y-axis, if any. So how do we do that? Now for that to be done, now instead of writing the degrees of x in each term, now we'll look for the degrees of y in each term. So if you look at it that way, the degree of this term involving y is 3, because this is a y cube term here. In this, the degree of y is 1. In this, the degree of y is 2. In this, the degree of y is 1. And in this, the degree of y is 0. And out of all this, which is the highest degree term in y? It is this term. Now equate the coefficient of this y cube to 0 is what we are supposed to do. So obviously, what is the coefficient of y cube? Because there is nothing along with y cube, we should take the coefficient as 1. But of course 1 cannot be equal to 0, right? So because we do not have any other thing, it is the expression is supposed to be in terms of x for us to proceed further, but because the coefficient of y cube is a constant, we will now claim that there is no asymptote parallel to y-axis. I repeat, now this is y cube, the coefficient of this is 1. Even if it were a 2, we couldn't have proceeded further because we cannot have 2 equal to 0. So basically, as long as the coefficient of this is not a constant, we should have proceeded further, but because the coefficient is a constant, I would simply say that itself, since the coefficient of the highest degree term in y is a constant, which is specifically 1, there is no asymptote parallel to y-axis. Again, we should specifically say that this is the asymptote to the curve. So there is no asymptote to the curve parallel to y-axis. So now to conclude, we have got one asymptote parallel to x-axis, which is y equal to 0, which is nothing but the x-axis itself, and we have got no asymptote parallel to y-axis. Okay, now we were supposed to get at most 3 asymptotes, out of which we have got only one. So we might have another 2 asymptotes. So now it's our job to find those 2 asymptotes. And obviously those 2 asymptotes are supposed to be oblique asymptotes if they are going to be there. Okay, so now we will start finding the oblique asymptotes. Okay, now how do we find oblique asymptotes? I'll now recall each of these steps. Okay, so first thing, group the terms in the equation of the curve based on the degrees in powers of both x and y. What do you mean by that? Now what is the equation that we have? The equation is y cube minus x square y plus 2y square plus 4y plus 1 equals 0. In this, look for terms particularly having degrees constant 1, 2, 3 and so on, and group them accordingly. So obviously the constant term is only this term, so this will be one term as it is. Okay, and then we have a first degree term which is only this, because this is of degree 1, and if you look at the second degree terms, there is only one term again, which is only this term. And then when you look for the third degree terms, they're going to be these two terms together, because this is of degree 3 and this is of degree 3, because degree of x is 2 and degree of y is 1. When we are looking for the degree here, we have to take the degrees of both x and y put together, not individually. Remember. Okay, so we have grouped these terms based on the degrees. After this, when we go for the step 2, what we are supposed to do is that we will have to find out something called phi k of m's. How do we find phi k of m's? In each term of degree k, take y equals m and x equals 1 and name the obtained expression as phi k of m. So accordingly, now we will start with the constant term. So we have phi naught of m. Now how do we do this? How do we obtain this? Simply look at the constant term. In this constant term, replace every y by m and x by 1. Because it's a constant term, there will be no x and y, so it will simply be whatever the number is. So phi naught m is 1. Okay, in fact, once you have got this, simply find out its derivative. It might be of some use later on. So phi naught dash of m is going to be 0. Okay, next, so this is the constant term. Now we go for phi 1 of m. So what is phi 1 of m? Phi 1 of m, as you can see here, is supposed to be 4y. In this, replace every y by m and x by 1. Because there is no x term here, this will simply be 4m. So replace y by m and x by 1. Okay, so this is what we have as phi 1 of m. And once you got phi 1 of m, find out phi 1 dash of m. Phi 1 dash of m is going to be 4, obviously. Similarly, go for phi 2 of m. What is phi 2 of m? Again, there is only one term. In this, replace every y by, I'll write that rule here so that you can remember it very easily. So replace every y by m and every x by 1. Now this is 2y square, so in that there is no x at all, so simply replace every y by m, and that will give me this expression phi 2 of m to be 2m square. Okay, so phi 2 of m is 2m square, so accordingly phi 2 dash of m is going to be 4m. Okay, and next we have to go for phi 3 of m, because we also have a third degree term, and in this now, as we can see, there are two terms. Now replace every y by m and x by 1, and that will give me this expression as m cube minus x is 1 and y is m, so this will be m cube minus m. Okay, do we have a phi 4 of m? Of course not, because the highest degree term is 3. The highest degree is 3, so the highest degree term will give me only phi 3 of m. Okay, so now this completes the second step in finding the oblique asymptotes. Okay, so second step would be this. Second step would be for each term of degree k, find out phi k of degree k, find out we have done phi k of m. That we have done. Now what next? The next step will be to take phi n of m equals 0, where n is the highest degree, and solve it. So coming back to the problem, yeah, I was supposed to do one more thing here. So once we got phi 3 of m, we should find phi 3 dash of m. What is phi 3 dash of m? This is 3m square minus 1. Remember. Now, as I said, the next step will be to now take phi 3 of m to be equal to 0, because this is the highest degree term. Okay, I'm just marking it this way so that you will be able to understand what this means. Okay, so take phi 3 of m equal to 0 and solve it, is what we are supposed to do now. So what is phi 3 of m? It is m cube minus m, and now take this equal to 0 and solve this. How do you solve this? This is a cubic equation. Accordingly, there are going to be 3 roots. But of course, in this problem, finding them is basically very easy, because if you take an m common, you are going to get m into m square minus 1 equals 0, and solving that will give us m equal to 0, or m square minus 1 equals 0, which will give us m equals 1 or m equals minus 1. Okay, so as I said, because this is a cubic equation, there are going to be 3 roots, and because we are going to get 3 roots, we have got 3 values of m, and based on each of these values of m, we are supposed to find the corresponding values of c, so that we get oblique asymptotes. Now how do we find c? So we find c based on the next step that we have. Okay, so we have completed step 3 by solving phi n of m equal to 0. Now we go for step 4. Step 4 says if m is a distinct root, then use this formula to find c. If m is a double root, use this formula, and if m is a triple root, use this formula, and so on. Now what is the nature of the roots that we have got in this particular problem? We have got m to be 0, 1 and minus 1. So we have got 3 roots, and each of these roots is a distinct root. Correct? 0 is a root which is distinct from 1 and minus 1. So 0 is a single root or a distinct root. 1 is another root and minus 1 is another root. So all the 3 roots are distinct, and because all the 3 roots are distinct, what expression are we supposed to use in these 3? For m to be a distinct root, c is this, right? So because each of the roots is a distinct root, we will have to use this expression to find out the values of c. Okay, so I'll paste this expression here so that we can use this everywhere, every time to find out the values of C. So what we now do is, for each m we'll find the corresponding value of C using this expression. Okay, now C, as you can see here, is given by minus. Now what is n here? N is 3. Okay, so I'll write that here. What do you mean by n? N is going to be the highest degree of the equation. So n is 3. So because n is 3, the formula simplifies to minus phi 2 of m divided by phi 3 dash of m. Okay, so now we'll use this formula to find out the corresponding values of C. Now what is phi 2 of m? Phi 2 of m, as we can see, is 2m square. And what is phi 3 dash of m? Phi 3 dash of m is 3m square minus 1. Correct? So now we'll use this formula to find out the values of C corresponding to m's. So first of all, when m becomes 0, what will C be? So replace m by 0 in this. So that will give me minus. The numerator becomes 0 and the denominator becomes minus 1. But because the numerator itself is 0, there is just no point writing a minus sign. So okay, so this will be 0 by 1, which is effectively 0. Okay, now when you go for m equals 1, which is the next value of m, then we get C to be, what will be C? Now replace every m by 1, so that will give me minus 2. M square is 1, so this will just be 1 divided by, again m square is 1, so 3 minus 1 is 2, and that will give me the value of C as minus 1. So when m is 1, C is minus 1, and when m is minus 1, this is the third value of m, as we can see here. So when m is minus 1, the corresponding value of C is going to be minus, when you take m is minus 1, m square is going to be 1 here, and m square is again going to be 1, so that again gives me minus 2 by 2, which gives me the value of C as minus 1 itself. Okay, so now we have got now we have got m equals 0 giving us C equals 0, m equals 1 giving us C equals minus 1, and m equals minus 1 giving us C equals minus 1. Therefore, now we say that the asymptotes of the curve are given by, how do we find asymptotes? As I mentioned earlier, the equation of the asymptote has to be of the form of y equals mx plus c. Okay, so correspondingly, when you have m to be 0, we have c equals 0. So accordingly we have y equals 0, because m is 0 and c is 0. That is one equation. If you remember properly, we had actually got y equals 0 to be one asymptote, which is exactly what we have got as the first asymptote. The next asymptote will be obtained by taking m equals 1 and c equals minus 1. So what do we get? M equals 1 means we have y equals x, plus c is minus 1, so accordingly this will be x minus 1. Okay, So this is the second asymptote, and the third asymptote is obtained by taking m equals minus 1 and c equals minus 1. So that will give me y equals minus x and then minus 1. Okay, so I hope you got this part properly. So take m equals minus 1 and c equals minus 1. That will give me y equals minus x minus 1. So these are the three asymptotes that we have got for the given curve. And can we find more? Of course not, because the maximum degree of the given equation is 3. So we can have at most 3 asymptotes, and because we have already got 3 asymptotes, there is nothing much that has to be done further. So this completes solving this particular question of finding the asymptotes for the given curve. Right? So this is exactly how we find asymptotes parallel to x-axis, asymptotes parallel to y-axis, and oblique asymptotes. Finding oblique asymptotes looks a little cumbersome, looks a little lengthy, but by practice you will be able to find values of m and c very easily, and that correspondingly will give you asymptotes. Right? So this is exactly how you find asymptotes to the given curve based on the general rule. Right? So with this, I'm going to end with this session. So go through this video carefully and try solving these two problems by yourselves in parallel, and also try to solve more problems so that you'll be able to understand things in a much easier way and much better way. Fine. Thank you for your patient listening. See you soon in the next video. Thank you.